All right. So yeah, after Bob's nice introduction to parallel computing, I'm going to talk a little bit about, give you a little bit about a hardware overview. The hardware that we have at SDSC, and how you can get some information about hardware yourself on the system, or basically any system. So with that, let's start. So this is actually in the data center. So Expanse, and I'll tell you a little bit more about Expanse as well. So most of you are here because you're computational scientists, and so you have a specific scientific problem that you're trying to solve, and or you're supporting researchers from a variety of domains, and that's what we are doing. The actual hardware at that point is probably of secondary interest for you. However, it's still interesting, although it's not that interesting for you. For many people, it is interesting. In particular, it's helpful to know a bit about hardware, so you can better understand how you get the best out of your codes, and when you're running simulations, you don't make any mistakes in terms of the compute resources that you're using. So what we're going to do in this talk, we will learn a little bit about Expanse hardware, and then how to get information about the system you are working on, and how to use some common usage monitoring tools. And I'll try to do this in about 40 to 45 minutes, so that afterwards we have a break before I'm going to tell a little bit about some useful Linux and tools. So we'll look a little bit at Expanse. You already know something about Expanse. I'll give you again a brief overview of the system, and then a little bit more details about the AMD EPIC processor architecture before we're looking at different ways of obtaining hardware information, and finally also look at TOP and HTOP, which you may already know, and if not, those are very useful tools. So let's start with a brief system overview. As you know, when you log into the compute cluster, so the way it works, so you have a remote access. So that's you. It could be in a laptop or a desktop computer, doesn't really matter. And when you log into a supercomputer or compute cluster, you will end up on the so-called head node. That's where you will also interact with a scheduler. And so the head node is interconnected with the compute cluster via a network. It's connected to the data storage. There are different file systems. Tell a little bit more about that in detail. And that network connects then all the different compute nodes. So there are many, many different compute nodes on which you will run the parallel tasks, as alluded to in the previous discussion. And when you log into Expanse, you basically get onto that login node. You are familiar with that. Here's again a brief overview of Expanse. It consists of 13 so-called scalable compute units that have a total of 728 standard compute nodes, and then 52 GPU nodes. So there's two different types of nodes, first of all, in Expanse. And then we have an additional 4 large memory nodes. So if you have special requirements in terms of memory for your applications, there is a limited set of those available. We say data-centric architecture, but basically what we mean is we have very, very high performance and large data storage capabilities. So there's a 12 petabyte performance storage that delivers a 140 gigabyte per second data transfer, can do 200,000 IO operations per second. And then in addition, we have fast IO node local NVMe storage. So I'll tell you a little bit more about that. And then there's the 7 petabyte set object storage. That's where the home directories are sitting. And this is all connected by a fast network. So those are the important pieces in terms of the hardware. Again, so this is how Expanse looks like. Now, in between the two different rows of racks, so there's actually 2 rows. Here you see on both sides, and here you see all the networking that's going on between the compute nodes. Looks pretty fancy if you're there. And this is the overview. I'm a little sorry for this. Is scaling up actually is a little bit hard to read now, but I want to tell you a little bit more about this. So the system layout. So we have these 2 rows that you've seen there, and in one of those rows, we have a core management rack. So if you look at this management rack, it has the login node. So if you log in, you end up on one of those login nodes, right? Those are connected to the NFS server, but all the compute nodes are also connected to the NFS server. And then here you have the network switches that connect the different racks with each other. And we also have the large memory nodes in this management rack. And then the compute nodes, they are in all the different scalable compute units. There's the regular compute nodes, and then we have the GPU nodes there at the bottom of the racks. These are all interconnected with very fast HDR InfiniBand switches. And so you get very fast connections between the compute nodes, but also between the compute nodes and the I/O nodes. So the special nodes that I didn't mention yet, they handle basically the data storage. And as I mentioned before, there's different types of data storage. So we have this object storage that's connected via a little bit slower FDR InfiniBand switch. That's where your home directory is sitting. And it's important to know that there's these different types of storage because first of all, you get less storage amount on those in your home directory, and it's also slower. While if you want to have high performance I/O and large data storage, you should use the cluster performance storage that's connected via faster HDR InfiniBand. And that's kind of also be used for parallel I/O operations when you have a code that actually is able to do that. So with some codes you can write in parallel from different MPI processes, and you would get high performance doing that on the cluster file system. And then finally, each compute node itself has on-node NVMe. So it's a total of 1.2 petabyte, but important pieces like each compute node has a 1 terabyte of local storage. And that local storage is really fast. So if you have code that does fast I/O or requires fast I/O, does a lot of I/O operations during the simulations, you need to make sure that you're writing to that local storage instead of the performance storage here, because it's much faster to do that I/O, local I/O operations. The login nodes, right? They are meant for file editing, simple data analysis and tasks and so on. And you shouldn't do anything on those that is computationally demanding. So if you have anything that's computationally demanding, you need to submit your jobs as discussed before and run through the batch queuing system. So you would basically get a login and either interactively, if you want to do something interactively, or via the batch queuing system, a job that then runs automatically once it gets scheduled for the time it needs to run on one or multiple of the compute nodes. So the login nodes should not be used for anything that's computationally intensive. So the login nodes are not the same as the batch nodes. So that's another thing that you need to keep in mind. For instance, if you compile code as well. And the other thing that you need to know is that the compute nodes are also different, the GPU nodes from the CPU nodes. I will not talk a lot about the GPU nodes here because we'll have a different presentation about GPU computing and programming. And I'll go into more detail about the GPU nodes in this presentation. Then let's look at, if you get onto one of the compute nodes, how the AMD EPYC processor architecture looks like actually. So this is just a schematic of the processor here. And so if you boil it down, we have 2 processors in each compute node, and each processor is a 2nd generation EPYC processor that consists of so-called core complex dies. So you see these CCDs here, there are 8 of them. Each processor has a total of 64 compute cores. So if you do the math, you can already see that we have 8 CCDs. So each CCD must consist of 8 compute cores. Those are connected to memory I/O and each other via the so-called I/O die. So there's a chip on there that is the I/O die, and it connects you to the DDR memory and to I/O. It could be I/O to the disk, for instance, right? And then there's 8 memory channels per socket. So each CCT basically is connected to different DDR memory. They can talk to each other via this I/O die, but there's some important differences in terms of latency and memory access, depending on where the data gets stored. I'll get back to that. So the memory and the I/O can basically abstract it into separate quadrants, the so-called NUMA quadrants, where you have non-uniform memory access, and each has 2 DIMM channels and 32 I/O lanes. Now, each of those CCDs has 2 core complexes. So there are 4 Zen 2 cores in each CCX, right? So as you can count here, there's 1 compute core, 2 compute cores, 3 compute cores, 4 compute cores, right? And so this is the entire CCD here. So if you go back, it's one of those dies here on the chip. And each of those cores in each CCX shares a 16 megabyte level 3 cache, right? So in total on the chip, there's 16 times 16 is 256 megabyte level 3 cache. But of course, each of those 4 cores, they can access, or they have basically their own 16 megabyte level 3 cache. And then each core includes a private 512 kilobyte L2 cache. So this L2 cache is accessible only for one of those cores, while this one is shared across four cores in total. And then you have like a total of 256 megabyte for each processor. Then, the 4 logical quadrants that we have, they allow the processor to be partitioned into different NUMA domains. That can be controlled by a BIOS, but these domains that are designated as NUMA per socket. So one socket is for one processor, right? So this is basically one processor, as we've seen before. So you see the CCDs here. And there are 4 NUMA domains per socket. It's a typical HPC configuration, and that's how it's set up, basically. So what that means is, we have non-uniform memory access, depending on where your CPU cores, which CPU cores you have your threads running on. And, that this allows you basically to schedule, and it should be done automatically, but it's something to keep in mind is that, if you have a thread that's running on one of those NUMA domains, it has a different memory latency to accessing memory than depending on where the data is stored. So the memory is interleaved across the 2 memory channels. Each logical quadrant is a NUMA domain. I mentioned this before, so that's this one here. And the other thing to remember is that PCIe devices will also be local to one of the 4 NUMA domains. So that's basically the I/O die that has the PCIe route for the device. This is the typical HPC configuration. I mentioned it as well. The workload is usually NUMA aware, so ranks in memory can be pinned to cores and NUMA nodes, and that's what typically happens. And some of the things, that you basically have to keep in mind, or should keep in mind when you launch jobs. For most instances and purposes, many codes will do that automatically with the setups that we have in Expanse. But if you experience slowdown or experience some performance unexpected performance degradation, that's maybe something to look into. And then in total, if you look at a compute node, so this was talking about a single processor, right? So I said each of those processors has 64 cores in total, and it consists of eight of these core complex dies per processor, with 2 core complexes per CCD. And therefore, this should be say cores in a CCX share a level 3 cache, and therefore NUMA domains per processor, right? So we have 64 cores, and each Expanse compute node has 2 of those processors. That means, we have 128 compute cores, and we have 2 GB of RAM per core. So that's a total of 256 GB of RAM. And then finally, there we have attached a 1 TB NVMe storage for fast scratch I/O that you should use if you have a lot of I/O operations during running of your code. That's often also the case, if you have a lot of small files, You know, instead of having those in your home directory or on the Lustre storage, you might want to copy those first into the local Scratch directory and then run your code on it. Otherwise, you know, you could have significant slowdown due to I/O operations being slow over the network, and or just simply being slow if the file system just cannot keep up with reading, writing too many files at the same time. And so those compute nodes itself, then they are interconnected with HDR and InfiniBand, so that we have you know, high performance data communication between compute nodes if you have an MPI parallel code that is able to support this. So I'll have some more details about that, but because it's important, I put it on here explicitly. It's important to understand the storage hierarchy on Expanse. The home file system, like I said, is mounted by NFS, and it's used to store small amounts of important data like source code files, for example. And so this is relatively slow I/O storage. It's not suitable for heavy I/O when running jobs. Keep that in mind. So just don't read and write a lot to your home directory. It's fine, you know, if you have smaller checkpoint files occasionally. If you have larger checkpoint files, you might want to use the Lustre file system, which is suitable for parallel I/O or also for larger amount of project files like simulation output data. And then we have the local NVMe storage that's limited in space, like I mentioned, but it's very fast because it's local on each compute node, and it's fast SSD and NVMe storage, and it should be used when doing heavy I/O during simulations. One thing to keep in mind is that the directory you get available by the scheduler made available in the Scratch directory is non-persistent, so it gets deleted after the job's finished. So it's really only to be used for temporary storage during while your jobs are running. So that's what I wanted to tell you about an overview of the hardware, so that we can look a little bit at how to obtain actually hardware information if you don't know anything about your system, or you know, during execution, perhaps you know you want to check some of the jobs while they're running and see what's going on. And why is this important? For different reasons, you may be asked to report details on the hardware in the manuscript, for instance, or a presentation or a proposal. Particularly, you know about the compute proposals, you need to show that you have an understanding of the system and the scaling of your codes and the requirements. So if you request computer time, that's important. But of course, it's also important when you're running the jobs so that you make sure that everything's working as expected. So you'll know what you're running on and can answer questions like, is the login node the same as the compute nodes? Of course, not, right? And how does one machine compare to another, right? So Expanse is, of course, different from other compute resources that are available, for instance, through the Exceed system. It will also give you a way of estimating performance, or get an idea about the performance relative to another system, right? So to think about it, all else being equal, a job will run at least as fast on hardware with faster clock speeds. That's not always true, but you know, approximately, you know, higher clock speed means, you know, your code should run faster if you have larger cache memory and if you have faster local drives. So if you do, you know, heavy I/O, like I mentioned before, and now you have faster local drives, so then of course your code will run faster. It always depends whether it's, you know, compute bound, memory bound, or I/O bound, the performance of your code. And yeah, so this is like a funny slide about, you know, computers are like hammers, just like hammers. There's a wide variety of computer hardware, right? And you can probably get away with using the wrong one, but your performance may be suboptimal and you might end up using a bigger tool than you need. So, or put differently, you know, you might have code that actually doesn't run very well on the hardware that you want to use, and then you're wondering why is that the case? So if you want to get some information about the processors, there's a command that's called lscpu. And on Linux systems, this command lists the key processor information. So you get information about the number of processors or sockets, right? So for instance, on Expanse, you should see that there are 2 sockets because we have 2 processors. And then information about the processor type of model. You get information about the clock speed, number of cores per processor, cache sizes, the instruction set architecture. So what does it support in terms of instruction sets, and information about NUMA nodes. So there's an example output here. If you go on an Expanse compute node and you were to type that command, so you see you get a lot of information. And like I said, so the important pieces that you see here, there are basically 128 compute cores, and there are 64 cores per socket. There are 8 NUMA nodes, like I mentioned before. So each of those sockets, each individual AMD processor in this case, has 4 NUMA nodes. And that's the type of the processor, the clock frequency, information about the cache, right? So that's available. So you see that was a total of 32 megabytes. So there's like 16 megabytes per processor. L2 cache, that's the cache that was available for each individual CPU core, right? And those are the NUMA nodes. So if you have like CPU core 0 to 15 are on NUMA node 0, and so on and so forth, right? And that can help you placing, for instance, threads and or MPI processes with an ideal way for your simulation, for your code to run optimally. And these are instruction set features that are available on the processor. So you see things like, for instance, what we see here are the SSE. There should be somewhere also AVX. AVX2 is supported. So these are advanced vector extensions. For instance, the processor can do multiple vectorized floating point operations in one clock cycle. And yeah, so that's basically interesting to know. And if you compile your code for one set of processor architecture, if the instruction sets included in your binary that make use of any of those, then they must be supported by the processor, otherwise the code will not run. Yeah, so those are the most important features. I should have gone directly to the slide, which is highlighted, but those are the pieces that are most important to look at. On Linux systems, there is also the proc CPU info pseudo file that contains pretty much the same information that you can get from LS CPU, but with a few differences. Here, the information is listed per core, and you get access to the instantaneous clock speeds. So the processor can ramp down its clock speed when it's idle, and then it can ramp it up when it's under load. And so you can check the clock speeds while codes are running. Right. So some other information about cache line flash sizes and other low-level details that you probably don't need to know about. But if you're curious, you can look at those things. So, for instance, what you can do here is you can do in this case we grab for CPU megahertz in proc CPU info, and you see that now, okay, there are 1, 2, 3, 4, 5. Okay, you look at the first 5 entries here, and you see that we actually have different clock frequencies for the different processors. So it looks like there's probably something running on these 2 CPU cores, and these ones are idling or are not under heavy load. So the processors are actually using less power. It's for power saving reasons. You see some information about cache line flash sizes, cache alignments, address sizes, etc., etc. So these are things that you typically don't have to pay attention to. It's also bugs, right? These were the famous bugs that were identified in Intel x86 processors and also AMD that have been addressed, fortunately, over time. Yeah, so that I think because I talked about before already cores and processors. So typically, what we think as of a processor is basically the thing that plugs into the motherboard, right? I mean, that's the chip here, and we have 2 of those in an advanced compute node, and each of those has 64 compute cores. And proc CPU info uses processor in a different way to mean as a compute core, right? So you have basically thinking of a multi-processor system. But typically nowadays we say, okay, a processor has multiple compute cores. So LSCPU in that sense uses a more intuitive terminology, right? Quick aside on simultaneous multithreading, so you might hear about that. It's called SMT. So this is the process of a CPU splitting each of its physical cores into virtual cores, if you want so, which are known as threads. You know, threads are basically you know, can run on different cores, but then you can have multiple threads also run on a single core, and this is done in order to increase performance by basically overleaving instructions. So you have to run 2 instruction streams at once, and so it can get a little bit of speed up. You'll never get a 2x speed up by doing that, right? Inside Blender, this process is hyperthreading, and it's really the same thing as simultaneous multithreading. So AMD CPUs with 4 cores, for instance, use simultaneous multithreading to provide 8 threads, and et cetera, et cetera. I mean, we do not enable hyperthreading. When you have hyperthreading enabled, the core count will appear to be doubled, right? We don't enable it because typically you don't get for high performance, you know, codes, compute codes that are, you know, any number crunching codes, you typically don't get speed up by running more than 2 threads in a single core. So typically that's disabled, but it's good to know about. You might be on other systems where hyperthreading is enabled, and then often you want to make sure that you actually use only half of the available threads in order not to slow down the code actually. Or in other words, you want to run 1 thread per available compute core, right? Or 1 MPI process per available compute core. Right, here a brief aside on pseudo files. I just mentioned it before, but haven't defined it. So it's good to know. So recall that in the Unix or Linux world, everything is treated as a file. So we have you know, files, directories, devices, etc. Everything is a file. So proc and sys are just interfaces to the Linux kernel data structures in a convenient and familiar file system format, right? So you did see here the /proc in the file system and /proc CPU info, and that file is actually empty. You see it has a 0 bytes, but you know, if you look into it, there's actually then information in it that you get from the kernel data system, kernel system. Yeah. So that was the proc CPU info data, and there's some information, you know, if you get information about the processor, often what we can do is we can look a little bit further in terms of the code names, what the processor means, such as Rome or Milan. You know, you can look that up at Wikipedia. You know, the proc CPU info pseudo file returns something a little bit more opaque, such as AMD EPYC 774 264 core processor, but you know, I mean, nowadays with Google, you pretty much quickly can find information if you want to know anything more about the type of processor, and you know, the architectures and what was the predecessor, what's coming out new, what is the successor if this processor is older, and so on. So if you like these things, there's a lot of information on the web that you can get a lot of details about the chip architectures. One thing that's important to know, and people often discuss about, is advanced vector extensions. So AVX, AVX2, AVX512. Before that, there was something called SSE. And the advanced vector extensions are basically an extension to the x86 architecture that allows a compute core to perform up to 8 floating point operations per cycle. so it's basically a vectorized operation where you have data parallel operations happening on multiple data at the same time in a single clock cycle, right? So you get a much higher computational throughput. And AVX2 improves this to 16 flops per cycle per core, right? So each core basically, instead of doing a single floating point operation per clock cycle, can do up to 16. The AVX512 further improves this to 32 flops per cycle per core. Now, AVX512 really means the 512 stands for 512 bits. So there's, actually, if you have 64-bit variables, so 64-bit floating points, double precision, that's like only 8 of them, or it would be 16 floating point numbers, right? 32-bit floating point numbers. And then you get to those 32 flops by doing something like a fuse multiply add operations. So not all operations would be able to do 32 flops, but an FMA operation would be able to do that. Right, these vector extensions were partially developed in response to challenges in increasing CPU clock speeds, right? So you couldn't, up the clock speeds. You see we've had in 2000, we had already 1 gigahertz, and we are still, about 3 gigahertz, and it's not, that's typically what processors run at. It's possible to have higher clock processors, but we're not anywhere at 100 gigahertz, and that's never going to come. So what we have to do instead is, parallelizing across cores, and then for each core we have a parallelization in terms of vectorization. And GPUs in some sense take this to the extreme. They are massively parallel architectures, and that's something I'll talk to you about on Thursday. So if we, we can, so there's a 2x speed up when going from a non-AVX processor to an AVX capable processor. Yeah, so these numbers, it depends. I mean, there's certainly a speed up, but your code has to be written in such a way that it supports these vector operations. Typically, this works extremely well if you have something like linear algebra, right? So like blast type operations, like matrix multiplication and that dense matrix multiplications, right? That sort of things. So the memory layout has to be matching so that you can take advantage of that vectorization. Often that requires people to rewrite their codes as well. It's a lot of the data has to be aligned in memory in a proper way for the processor to be able to actually make use of these things. But if you go basically from AVX to AVX2, it's a 2x, and then from AVX2 to AVX512, in principle, you get another 2x. And Xpans doesn't have AVX512, it has only AVX2, but you shouldn't worry too much about that, because first of all, there's not many codes that really can take advantage of that. The other thing, so it's hard to make good use of these AVX extensions, although they are very important, and some codes do, but not all codes. The reason is you need these long loops with vectorizable content, and the memory bandwidth also needs to be keeping up with that, right? The other thing is on Skylake processors, for instance, the clock speed is scaled down when AVX512 instructions are issued. So you get more throughput, but the processor is clocked slower, right? And simply because, when it just consumes too much power, it gets too hot and it clocks down. So the speed up is not really 2x that you get. So it's not really much that we lose on Xpans by not having AVX512. On the contrary, we have very good performance because we have many more compute cores than typical Intel processors at the time. So that's what I wanted to tell you about processors. Already 9:53. Let me see how many slides. Still a few slides to go through, but we should be able to finish in time so that we can have a short break. So if you want to get memory information, you can look at procmeminfo. That's a pseudo file that lists key memory specs. There's probably also, again, more information that you want, but there's at least one bit of useful data. So you get the total memory, and there's a pretty good approximation, this active memory here, to the memory that's actually in use by some applications on the that's currently running on the compute node you're on. So that means that using a simple script, you can monitor the total memory usage for all processes as a function of time. But of course, there's a lot of discussions on how to precisely measure memory usage. So, but if you're on a dedicated node where you yourself and nobody else is running, there's a script here where you can use that script, and if you have time, you can walk through that yourself and or ask questions later. I don't want to go through this now. It's a PostScript, but that you could use, and you get information about the memory usage while running the code or some codes on a compute node, and that could be quite informative. There is also DMI decode as a command that is you can use if you really need to dig deeper and get more details on memory configuration. But you'll need root privileges to do this. So you won't be able to do that on Expanse, but maybe on some other type of computer that you have access to. And so there's much more information about the different, in memory banks and the type of, the speed of the, you see details about the memory. It's a DDR4 memory that is running at a clock of 2.1 gigahertz. You get serial numbers. If you have memory corruption, you could figure out which of your DIMMs, for instance, is broken and in which sockets it's sitting, and so on. A lot of information that you can access if you want to. Now, GPU information. Sorry, this is now here in between, but I'll tell you much more about that on Thursday. It's just there's a command that's called, if you are in a GPU compute node, there's a command that's called NVIDIA SMI. That's the system management interface for NVIDIA GPUs, and that will give you information about the GPUs. So you see the type and the count of GPUs that are available to you. In this case, we have only one GPU. There's a Tesla V100 SXM2. So those are the GPUs types that we have in Expanse. If you run these in the GPU shared partition, you will only see the GPUs you had requested. So remember, I told you that there are 4 GPUs in each GPU node, but you don't always want to use all the GPUs. Instead, you want to use only a single GPU. If you, for instance, your code just runs on a single GPU, right? It's not parallelized across multiple GPUs. And then you run in the shared GPU queue to request a single GPU. And if you run NVIDIA SMI, that's the GPU that you will see. And that also means, if you launch a job that actually executes on an NVIDIA GPU via CUDA, for instance, or OpenACC, so code that has been written for GPUs, for NVIDIA GPUs, it will launch on that GPU, right? In this case, it says there are no running processes found, but if you have a process running, it would tell you that that process is running on that GPU, and then you would probably see the temperature go up because it becomes, the processor becomes warm, the fan speed going up, the power consumption going up as well. If you have a compute intensive code running on a GPU, it will draw up to 300 watts in this case. And of course, it will consume memory. There's a total of 32 gigabytes of RAM on each GPU. And that memory is different from the system memory. Still have a lot of slides. We'll go a little bit quicker over the cache information. You can obtain cache properties through /pseudo file system. The basic information between different vendors should be consistent there. And again, get information via LSCPU, but here you have some more information. And so here we, for instance, navigated into the sysdevices system CPU directory, and then you do an ls, you get information for all the different types of CPUs, and there's like what the frequency, etc., etc. So if you look into for each CPU, so CPU 0, where CPU here is a CPU core again, and look at the cache information, you see you get a lot of information that specifically about all the cache, the size, the type, power consumption, cache coherency lines, and shared CPU mapping, right? So which CPUs, other CPUs have access to that cache memory. And so if you look at, the expanse cache properties I told you before, so there's L1 and L2 and L3 cache. L1 for data and instructions, that's the line size. There's a total of 32 kilobyte for data and instruction cache sitting right on the chip, right on each core, CPU core, and then you have this 512 kilobyte of L2 cache memory, and then the L3 that's shared with other processors on the CCX, on the core complex, right? The 4 cores that I mentioned before. And so on those slides, there's some information about cache memory sizes for previous computers that we had at SDSC. That's was an Intel Haswell processor. That was the predecessor of Gordon. And you see that, cache sizes become a little bit smaller. And then Trestles was a previous AMD system that's the predecessor of Gordon. That again had a little bit larger cache sizes actually as compared to the Gordon system. And you can see then the impact of cache sizes on the performance. So this is here an example based on the old systems that we had. So you see compute time for Trestles and Gordon. So these are old machines. Like I said, Trestles is actually the older AMD system. And here is a DGS-EB. So that's a solver for solving system linear equations. So it's basically a dense linear algebra problem. And the n is the dimension of these matrices, of the matrix A, I believe. And you see the ratio. So in principle, I think Gordon should be a factor of 2 approximately faster, but it's not the case actually for small systems that fit into the cache memory on Trestles, but not on Gordon. So basically, Trestles mitigates performance impact for very small problems because it had a larger cache size. So sometimes, you can see that if you have more cache, of course, your code can run faster up to certain system size. And once it goes out of the cache memory, then, the newer system is going to be faster. You can get SCSI device information on proc SCSI file. So that's typically information about the attached disk storage, right? So in this case, we have 1 terabyte PCIe and NVMe disks, and you would see that with the ls SCSI command also. That looks, or you can look on the proc SCSI file. And so you see, on Expanse, we have basically 1 terabyte NVMe available, flash drive. Then df is an important command on file system usage. So if you type df, you'll see information about the free disk space, so disk free, and -h for human readable. If you type that, so you'll see if you're on a compute node, you'll see this def device, so mounted on def NVMe 0 N1 T1. So this is about a terabyte size, like I told you, and it's mounted on /scratch, right? So that's the local scratch memory. Then we have here file system that's mounted at /expanse community and /cm share. So that's SDSC maintained software stacks. Then we have the Lustre and project scale project file system. So the Lustre scratch and project file system. So those are the ones that are in the not node local, but they are our high performance file systems. And you see there's a lot of data available. So total size of 11, well, it's really about 12 petabyte. And you always see the used and available memory. So here you can store more data. And then finally, the home file system, that's the one, where you might want to keep your source code and other important files that are also backed up. So you want to make sure that you don't lose the data, but you only have limited storage. So if you have limited storage and the performance is slower than the /expanse projects and /expanse scratch Lustre file systems. Okay. So don't do a lot of heavy I/O in this home file system. Don't do any, don't read and write a lot of, small files. Otherwise, your jobs will run very slowly, and you will annoy other users because the file system will get slow. You can also get network information if that's of interest to you, using the IP command. So there's /svn-ip. It's usually used by system administrators, but you can use that and learn about networking information, and you see different information. So there are Ethernet adapters. You see those here with their IP addresses, and you see the InfiniBand adapter that's used for the high performance communication between the compute nodes. And with that IP command, you can there's many options to it. So you can get less information than this. You can look at only the IP addresses, for instance. That's the only thing you're interested in. Then if you want to have information about the operating system and the kernel, you can use the uname command. So uname -r gives you the Linux kernel version. Uname -o gives you, the system, the type of operating system you're running on. And -a, that's all the information. So you have more information. You're running Linux, you're on the login node. That's called login 01. Here's the kernel version. And it's a GNU Linux system. And then there's in /etc, there's files that give you information about Linux distributions. For instance, if you're running CentOS, then there's the file that's called CentOS release. So there should be /etc. I believe it's called Linux release. I don't recall. There are a bunch of different types of file names. CentOS is derived from Red Hat, so there should also be a /etc Red Hat release file that gives you information about the upstream version that CentOS is based on. But that's important, so you know which Linux version you're running on. And then, so we looked at a lot about machine info, and the question is, gone a little bit deeper than this is necessary for you to be an effective supercomputer user. But think of this as a way to round out your HPC knowledge. You're learning a little bit about the tools of the trade and getting comfortable looking around a system. And with that knowledge, it will make it easier to work with your sysadmin and picking up the background that will help you to make intelligent decisions in the future about how to run your codes, or if you have performance issues and you want to dig deeper on what's going on. So we don't do this exercise interactively now, but you can grab an interactive node or just a login node and experiment with what we've covered here. The login and compute nodes are different, of course, as I mentioned, and as you are well aware. And there's a cheat sheet here, with the different files here, file or commands to issues, the files to look at or commands to issues, and the information that is being provided. So, can be fun for you to play around a little bit with that. And then finally, I want to very briefly go over top and HTOP tools. That's pretty quick. If you're not if you don't know this, so the top utility is found on all Linux systems and provides a high-level view of running processes, right? So it doesn't give any information at the source code level, so you don't know whether the code that is running is efficient or not. So you'd have to profile your code for that. But it's useful to answer questions such as, how many of my processes are running? Or threads, and what are the states of the processes? Are they running, sleeping? Do they consume actually processing CPU time? Which of the cores are being utilized? Are there any other competing processes that may be affecting my performance? So, for instance, if you are in a shared compute node, all right, and what fraction of the CPU is each process using? How much memory does each process use? And is the memory usage growing over time? So, you could identify memory leaks, for instance, doing that. And how many threads are my processes using? So its top command is customizable. So by default, you get the processes information, but no threads. And to toggle the threads display, you can type H while top is running. So you run the top command and then you H, and you'll see the information about threads. You will get information for all users, but you can restrict this to a single user. So, if you have multiple users on a compute node or, on a system, you just type top minus U username, and then you'll see the processes only and threads only of that user. And so you'll see process ID, priority, the nice level, virtual memory, physical memory, shared memory, the state of the process, the percentage of the CPU that's using. That's probably what you mostly want to look at, and the percentage of memory, and then how much CPU time it has used. And to modify what you see, you can type F while top is running, and then you can toggle the fields using different methods. And by default, it updates every 3 seconds. And you can change the refresh rate by launching this top minus D N. So that's quite useful to know, I think. And what you also need to know, it's usually ordered by CPU usage. So you'll see the processes that require most of the CPU usage or are using most of the resources on top first. You can type M, and then your processes are ordered by memory usage. So you see the processes that use most of the memory, right? So if you type top, you'll see an output like this, and so you see the, what we see here, 16 processes. Each is using anywhere between 21 to 100% of the compute core, right? So 21, and these ones, really using the CPU core. Okay. The memory footprint here in this example is minimal, with each process only using up to 76 megabyte, right? So you see in percentage of memory, that's almost nothing. So you see here the resources being used, memory resources. And the CPU times are ranging from just 11 seconds, just started, right? So this one just started, to 1 hour and 31 minutes, actually, right? So one of these processes has been running for a long time. And so if you have a threaded code and you have the thread display toggle to the off position, then you see something like, oh, wow, this uses 1,600% CPU. That's not, it doesn't mean it runs on a single core, but it should be running on multiple cores. So that would be a process that has, for instance, 16 threads and it's running on multiple processes, right? So, but what we see here, and then if we look at this in detail, is, we see that one process is making good use of CPU and the other one's not, right? In this example. So this is information that you can get out of top. And here's an example where you have 16 threads that all make good use of the compute cores. Not perfect, but at least pretty reasonable, I would say. Okay. And then there's the htop command finally. So if you launch it, it looks like this. Occupies your screen because we have 128 CPU cores. So it's like top, but with better interface, I think. And it has vertical and horizontal scrolling, process tree view, etc. A lot of options. And here you can see, the mapping. So visually as well, you see something's running 100% on CPU core 1, etc., etc. And so almost all CPU cores are running at 100% utilization, and only a few of them not fully utilized. And here's an example where you see that the CPU cores are not utilized to the full extent. And right, so once we do hands-on session or exercises in other sessions, you can open a terminal and run top or htop, and otherwise, you can use the login node or interactive nodes and play around with these options that we've seen here. One final useful tip here on Expanse. So once Slurm has allocated a node to your account, you actually also can log into that node. So if you have a batch job running, you can actually SSH into your node that's allocated for you, and then you can check is your code running properly using top and htop, for instance. And with that, actually, I'm done. Yeah, thanks for listening. And then I'll continue with some intermediate Linux information about things that could be useful to know.